So we learned in the last video that way long ago, mathematicians realized that derivatives and integrals are inverse operations. One involves the limit of quotients and the other involves the limit of a product. So because they're inverse operations, they undo one another. So we're going to keep that in mind when we go over the theorems in today's video. So first, we're going to talk about the average value of a function. When we see this word average, hopefully that reminds us of what we did like in middle school when we add up all the values and divide by the number that we had. Remember from chapter 4.3, we learned that when we're integrating, we're really finding the limit of the sum of area formulas. And we're trying to figure out what happens as n approaches infinity of this length times width. We did this with Riemann sums. And with Riemann sums, we just added up a certain number of rectangles. When we're integrating, we're actually saying, what if we could fit an infinite amount of rectangles and get the exact area? So when we're integrating, one thing we need to understand is that we're really adding together a bunch of values. That's what integration is doing. So when we see this piece of the formula, this piece is adding up all of these y values, and then this piece is dividing by the space between our shape. Okay, so it's nice to understand the formula because it helps us remember it. If you don't understand it, you could just memorize the formula and apply it and you'll be just fine. Okay. The second fundamental theorem of calculus is used whenever we are taking a derivative and an integral in the same problem. So remember, we talked those are inverse operations, meaning they undo one another. So think of it as if you had 10 plus 3 minus 3. Hopefully you see that these are inverse operations and they're going to cancel and we're left with the number we started with. If you didn't realize that, it's not the end of the world. You could do 10 plus 3 and then you could 13 minus 3 and come to the same conclusion. The shortcut just saves us a little bit of time. So the shortcut is realizing that those are going to cancel. And so that's kind of the idea on the second fundamental theorem of calculus. If we have to take a derivative of an integral, because they're opposite operations, they're going to end up canceling, and we're always left with a function that we started with. In the process, though, if we were to do the problem, this guy would end up getting plugged in, because that's what we do when we integrate. This would also end up being plugged in, but it's going to be a constant. So then when I take the derivative of a constant, it will go to 0. Also, when I take the derivative, I do have to consider the chain rule. So kind of the short version, and we'll talk about this more during class, but I would kind of use this version in the box. Okay, this is going to be a constant. So we're not going to worry about him because the derivative of a constant is 0. Okay. What we do need to worry about is whatever's up here, we're going to plug it in. So this becomes f of u, and then whatever we plugged in, we need to then take its derivative as we do in the chain rule. Okay, so that's the second fundamental theorem of calculus. Again, we can talk later about why we do what we do in that theorem. Okay, for now, we're just going to practice applying it. So if we were to actually apply the theorem here, this says find the derivative of this function. Okay, well, this function is an integral. So when we take the derivative of an integral, what ends up happening is that these cancel. I'm going to be left with the cosine of t, but if I were to do this the long way, this guy ends up getting plugged in. So cosine, instead of t, it's going to be of x squared. And then whatever we plugged in is kind of like a baby. So then we need to multiply by its derivative. And then the derivative of this is obviously f prime. And that is the second fundamental theorem of calculus. Again, we can talk more about why that works the way it works when we get to class. And let me go through it just one more time. Okay? So, because it asks me to differentiate this integral, the derivative and the integral will end up canceling. I'm left with the integrand. In the process, I plug this in, So I get cosine of x squared. And then since this is like a baby, I multiply by its derivative. And then the derivative of f is f prime. Okay? The last example we're going to talk about is the average value. Again, when we see this, hopefully we think of adding all the values and dividing by the number we have. So I need to add all of these y values together. So the way we do that is to integrate. So I'm going to add up 3x squared minus 2x from 1 to 4. And so that adds them all together. Now I need to divide by the number I have. Now we can't really divide by an infinite amount of numbers. So what we do here is we divide by the space between 4 and 1. And the space between is 3. So I need to divide by 3. Now this looks really messy and complicated. So what we do is we actually bring this out here, and instead of writing divide by 3, I'm going to write it like 1/3. And this is my average value formula. And all we do is integrate using the fundamental theorem of calculus. And that 1/3 is just going to kind of hang down for our answer. So we're going to add 1 to our exponent and divide. Here, again, we're going to add 1 to that exponent and divide. And we're going to evaluate from 1 to 4. This is the same example we did in the last video, except this time we have the 1/3 in front. Okay, so if we leave our coefficient in the front, we're going to have 4/3 minus 4 squared, Okay, and then I'm going to minus, and I'm actually going to leave this 1/3 in front of the whole thing. We're going to minus 1 cubed minus 1 squared. And then when we evaluate, remember 1 minus 1 is 0. Here we'll have a 1/3 times 64 minus 16, or 1/3 of 48. And if I divide 48 by 3, I get 16. This is the average y value of the function.